Welcome to Earth Science, everybody. Here we go. Time for igneous notes. Let's really briefly, though, just see how this thing's organized. So you're going to have an assignment that's called Rocks Labs. Within that, there's the 3 different Rocks Labs. These are kind of like, here's your rock kits. If you were the sort of normal year and you were in class, here's a bunch of rocks, and this is what we're going to work on, right? So when it's time for those, it's all in one assignment. You'll have to go back, but I'll keep it all linked. As long as you're using survival guides, shouldn't be too confusing. Just make sure you open up the right one for the right lab. Otherwise, it will be very confusing. Notes. It's one big document with a whole bunch of notes. So we're going to cover little bits of it in individual videos. We're not going to sit here and do however long this thing is all in one go. I think it's like, I don't even know if we'll do all of it. It's 14 pages. So again, wherever the video is cut off, that's going to be good. I numbered the pages, and then I also numbered all of the questions in here because they're stolen from various sources. So I numbered those all in red because I think I'll refer to those in other homeworks. All right, that's how it's organized. Follow the survival guides again. You're going to be fine. All right, so we're going to start with igneous, which is, of course, I'm not going in the order that I had set up here. Some years I do minerals first. Some years I do rocks first. This is a rocks first year. So we're going to go igneous. All right, now, hopefully, because you've done a little bit of rock cycle work, the vague idea is out there that igneous rocks, I never know where to put my little head. All right, here we go. Rocks that form from the solidification which requires a cooling of magma or lava. And again, magma, we call it when it's under the ground, lava when we call it above the ground. That might sound like a subtle difference, but it's actually going to be important in just a few minutes. So your job, and we're going to do these notes, then we're going to do the lab, and your job on the lab is going to be to really pick out and understand these 2 things. You've got to be able to understand its composition. I-T-I-O-N. What makes up that rock? And you got to be able to do that just by looking at it. That might sound intimidating right now, but actually with igneous rocks, it's very easy. Igneous rocks, like look at this reference table. This is the hardest reference table for all the rocks. There's a whole bunch going on here, but actually the rocks themselves are the easiest by far. So that's why I like starting with them, because the characteristics of these rocks, you're going to see they stick out like a sore thumb. So when you get your tray of rocks, quote unquote, which is a Google Doc with pictures, you're going to have to tell me about the composition of all of the rocks on that document. If it sounds intimidating, just hang on. You'll figure it out in a few minutes. And the rock's cooling history. In other words, did it cool quickly or slowly? And there's a very easy way to tell, again, by looking at the rocks. You guys are going to nail this. All right, so we're going to do these two things separately. Composition, let's start there. We'll do it in these boxes. The compositions you have, and again, if you did your work the other day, which you should, don't do this if you haven't gone back and finished the rock cycle stuff. The compositions we have are felsic, intermediate, and mafic. Now, if you did the right thing and you were working through this, you found felsic over here, you found mafic over here. Intermediate, it was actually, I should not have put it on that last worksheet because it's not written on here. What it's going to be is right in the middle of these two, the intermediate composition between felsic and mafic. So how can we tell? And what this is what minerals are in the rock, and then even so far as what elements are in them. And this is where, if you really learn these reference tables, I said this the other day, the rocks unit is the easiest one of the whole year. Because if you just learn how to use these and learn where things are hidden, the test is like a freebie. All of the information you want is just sitting right there for you. So if you see that felsic rocks are rich in Si and Al. That's silica and aluminum. Just as a quick side note, if you ever need to know the elements themselves, hey, I don't remember my periodic table. There's not a full-fledged periodic table in here, but the very, very last thing on the reference table is all of the ones that we might use here in Earth Science. So Si, silicon, Al, aluminum. All right. So felsic compositions have that. Mafic compositions have more iron and magnesium. So yeah, let's start with that. felsic, Si, comma, Al, mafic, Fe, comma, Mg. Now, if you're sitting there saying, what the heck, I'm not going to be able to spot this. Yeah, you're not. You're right. That's not super easy. So what else have we got? Well, this is another one that unfortunately, since you're home, you're not going to be able to experience, but don't worry, there's one that's going to make it easy. The density. The mafic ones are higher density. The felsic ones are lower density. And it's as plain as day. And if you're here in class and you really want me to, I'll go dig out some of the rocks. If you felt two similar rocks, one on the mafic end, one on the felsic end, you can, like, just by the heft, you know which one's more dense on the mafic end. All right, so we'll throw that in there. Now, is this stuff you have to memorize? No. The stuff that they might ask questions about? Absolutely. But all of that information sitting there right on the reference table, so it's always available to you. You pull it up, and there you go. Now, intermediate's kind of in the middle. Don't worry about it for now. We're okay. All right. How am I really going to be able to do this? It's going to go by the color. The color of felsic rocks tends to be lighter. The color of mafic rocks tends to be darker. Let's also note down here, all these crazy words that might be difficult to pronounce. These are the minerals that make up the igneous rocks. These are the igneous rocks up here. These minerals are in the rocks. So if you notice right here that we've got the potassium feldspar has pink. Pink only appears over here on this felsic end. You've got pink, clear, white, white, gray. Yeah, a little bit to black. That can happen, but look at how low the percentages are. So mostly pinks, whites, and grays with little bits of black. That's going to be our giveaway. So what we want, and this is the thing. So what you'll look for when it's time for the lab is a light color. So we'll say pink is common. It can be felsic and not be pink, yeah. But if you see pink, no doubter, you're over there in the world of felsic. Okay? Mafic. And again, let's do a start, because this is the thing that, like, when you're doing the lab that you're going to have to see. Dark color. That's it. So how about in the middle? What you're going to have is it's in the middle. It's not light. It's not dark. It's somewhere in there. So once we talk about what some of the other features are, what you're going to see here is either gray or half black, half white, like 50-50, half black chunks, half white chunks. Then you know you're in the middle between light and dark. If you see mostly light with some pinks, that's felsic. If you see mostly darks, you're mafic. But if you see about half and half, or you just see kind of grayish, you're in the middle. Okay? We won't worry about the in-between, compositions. They're just in between. Okay? So yeah, that's half the battle right there. And I know this video is probably getting long, but it's that once you get through this, you're going to find this lab. You're going to go boom, 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 boom. People, like, this is also the first... you guys have caught up with where we started COVID stuff last year. So people that had earth science last year, when we got interrupted by COVID, started with this stuff, and they did great. Like, this is all very figure outable from those pictures. You guys are going to do great. Okay. Lighter color, darker color in the middle. Okay. And that's going to determine where we are left, right on this chart. Are we over here for felsics, meaning that maybe we've got those rocks? Are we over here for mafics, meaning maybe we got those rocks? Or are we in the middle here, meaning maybe we got those rocks? All right. So that's half the battle. Now, how do you tell the difference from the top of this to the bottom of this between obsidian and pegmatite and all of those? So if you know your felsic, how are we going to go up, down here? And that's going to be by the cooling history. How quickly or slowly did this rock cool? So what I tried to draw here should have been similar to what you saw in the first rock cycle diagram, is that melted rock, being buoyant, being less dense, works its way towards our surface, likes to rise. Sometimes it doesn't make it all the way there. Sometimes it goes into these bubbles, which we'll call plutons. So if these form and then the top of the mountain erodes away, you can get a feature on Earth's surface called a pluton. I was on a cool one down near Asheville, North Carolina. Giant, big granite body forming within. Those are intrusive rocks. Other times, It comes right out of volcanoes. Those are extrusive rocks. So intrusive igneous, extrusive igneous. And what's the implication here? If it comes into this little bubble here and it's not exposed to the freezing cold air, and when I say freezing cold air, I'm talking if you're liquid magma, it could be a real hot day in Hawaii. But if you're magma, that's some cold air. Okay? This doesn't get exposed to that. This is trapped within the earth and insulated like a giant thermos. So what happens then is that this is very slow cooling. I'll blow this up so you can see it down here. These intrusive igneous bodies are slow cooling, whereas the extrusive ones, the ones that come out on the surface of the earth, are very fast cooling. And you got to be able to spot that. You're going to pick up a rock on that document again. You're going to look at a picture, and I want you to be able to spot the difference between one that cools quickly and one that cools slowly. So what are you going to look for? Well, if you cool very slowly, remember all these minerals down here that make up the rock? These are going to have time to get bigger and bigger and bigger. Quartz is formed of silica and oxygen. Each individual atom of silica and each individual atom of oxygen have to link up and hook up. And if it cools very rapidly, they don't have a whole heck of a lot of time to get very big. So if you want to get one of those nice big fat quartz crystals, as it gets larger and larger and larger, you're going to need time as that rock very slowly cools down. So what we refer to this, let's say that there are large visible crystals. And then the technical term that's used on the reference tables and used here in the world of earth science is that this has a coarse texture. And that means that there's large visible crystals. Let's get one thing out of the way here. Texture in the world of most of this, certainly in the world of igneous rocks, is not how it feels. If you talk about the texture, like the texture of this mask, it feels like blah, 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 versus the texture of this beaker with those little things on there, it feels like this. That's a common mistake because that's not how it works in earth science. If I take a piece of granite, if I go out into back down to that Pluton in North Carolina and I bring a rock hammer and I smack a piece of that granite out of there and I hold it in my hand, it's going to be all rough and jagged. That's how it feels. If I take that same exact piece of granite and polish it off, go through abrasion, it's going to feel smooth. That doesn't change what rock it is. It's still granite. So when I refer to texture, the way a geologist states texture is that they're talking about what do the individual grains within that rock actually look like. All right, here's your lab. Coarse texture, I can see bits here. Coarse texture, I can see bits here. Fine texture, I can't. Coarse texture, I can see bits here. So if you can see the bits, if they're visible, sorry, those are your other labs. If you can see the bits, the only way that they formed is if they had time to form because it was intrusive and very slowly cooling. Intrusive interior of the earth, all of that jazz. What about fast cooling? So maybe it's a lame comparison, but I've always used it. If I gave two groups a 100-piece puzzle, and I gave one group a full double period, 80 minutes to do it, and another group just the break in between classes, 3 minutes to do it, which one do you think is going to form bigger chunks of that puzzle? It's going to be the group that has more time, right? If you only have a couple minutes and you got to cool and form minerals, you don't have time to form those nice big visible crystals. So you end up with a couple options. Small crystals, like you can't see with naked eye, which is what we call a fine texture. All right, fine texture. I can't make out the bits that form that make that. That one, these two should both be fine. 7 looks like there are some little chunks, but for the most part, it's fine. Okay. Can't really see the bits that make up that rock. So how about this? I'll tell you that number 1 and number 8 down there are the same composition, but they cool differently. So they both have pinks and whites and blacks in them. 1 had time to cool nice and slowly and form all those nice big fat crystals. 8 did not. 8 just had to form a rock very quickly. That's an extrusive version of the same composition of magma. Yeah. A couple other things can happen. Let's just switch colors for the heck of it. What you can get is when all that pressure comes off really quick, if you've ever opened up a plastic bottle of soda that's been shaken a little bit, you experience foam. That's because the carbon dioxide under pressure inside that liquid suddenly can escape, and it makes the soda foam, right? Magma sometimes can do the same thing, so you can get foam. Now, we're not really going to call it foam. We call this a vesicular texture. That's the real term. Holes like Swiss cheese. Or you can get a glassy texture, which this is the like people hear this once and they memorize it like obsidian. It's always a lot like, just in my experience, people come to earth science with that little nugget in their head ready. So you're going to look for any one of these three. These will all indicate extrusive or fast cooling. And you don't really have to like differentiate anything else between them. Just those are on the fast cooling side, big crystals are on the slow cooling side, and you're good to go. Okay. Swiss cheese, vesicular texture, glassy texture. All right. So I think I'm going to stop quick. Well, no. I'd like you to do this. And here's what I'm saying. I'm going to do one of the 6 for you, and then I'm going to stop this video, and I'd like you to finish the other 5 boxes. So if it's extrusive, what's it like? If it's felsic, what's it like? So extrusive in general is going to be a fine texture. Felsic is going to be a light color. That's really the lab. There's 8 rocks in that lab. Here are 6 of them. I promise you I'm giving all 6. So you're going to have already described what those 6 rocks look like before you get to actually doing the lab. Okay. I'm going to stop. We got more to do. We're not done, but I'm going to stop, fill those out, and then let's go on with the next part. Oh, 17:45. We're going long. Great job, folks. Keep it up.